In this video, we will prove a problem given in Appendix B of the book Introduction to Algorithms by CLRS. The problem is this: reword each of the following statements as a theorem about undirected graphs and then prove it. Assume that friendship is symmetric but not reflexive. What is meant by symmetric? Symmetric means if A is friend of B, then B is also a friend of A. Not reflexive. Not reflexive means A is not a friend of himself or herself. Okay. So what is the statement which we need to reword? The statement is this: if everyone in a group is the friend of at least half the people in the group, then the group can be seated around a table in such a way that everyone is seated between two friends. This reminds me of something called Hamiltonian cycle. What is a Hamiltonian cycle? A Hamiltonian cycle in a graph is a cycle that visits every vertex in the graph exactly once and returns to the starting vertex. Graph containing a Hamiltonian cycle is called a Hamiltonian graph. So given that we know what is Hamiltonian cycle and what is a Hamiltonian graph, we can reword the given statement as this theorem. If G is a graph with n vertices with n greater than or equal to 3, and the minimum of the degrees of all the vertices of G is greater than or equal to n by 2, then G is a Hamiltonian graph. So we have to prove this. To prove this, we'll use another lemma, and that lemma is this: if degree of each vertex of G is at least n by 2, which is what we are given in the original theorem which we need to prove, the minimum of the degrees of all the vertices of G is greater than or equal to n by 2. So this is what I've just reworded that. If degrees of each vertex of G is at least n by 2, then G is connected. To prove this lemma, we'll use another lemma, and that lemma is easier to prove. That lemma says if sum of degrees of each pair of non-adjacent vertices is larger than n minus 2, then the graph is always connected. So let's assume that the opposite of what we need to prove in lemma 2 is true. Let's assume that the graph is not connected. For that, let's first understand what is connected. By connected, I mean there is always a path between any two vertices of the graph. So if opposite is true, then there will be two vertices u and v such that there is no path between u and v. If that is true, then all the neighbors of u will be different from all the neighbors of v, and u will also be not adjacent to v. If that is true, then u and all its neighbors can be put into one set, and v and all its neighbors can be put in another set, such that the two sets are disjoint sets. Okay. If that is true, then let's add the total number of elements in these two sets. That will be x plus 1 plus y plus 1, where x is the degree of u and y is the degree of v. Degree means the number of friends in this case, but in general, number of adjacent vertices. So if we add these two, x plus 1 plus y plus 1 is equal to x plus y plus 2, which is greater than n minus 2 plus 2, because in lemma 2 we are given that sum of degrees of each pair of non-adjacent vertices is larger than n minus 2. So we know that x plus y is larger than n minus 2, hence this whole thing is larger than n. We are actually saying the sum of the total number of elements in these two sets is larger than n, which is not possible. Hence the opposite of what we need to prove in lemma 2 is not possible, and hence lemma 2 is proved. Let's now try to prove lemma 1. In lemma 1, we are saying if degree of each vertex of G is at least n by 2, then G is connected. If we are given then if degree of each vertex is at least n by 2, then will this be true? Will this be true if sum of degrees of each pair of non-adjacent vertices is larger than n minus 2? What is the minimum sum of degrees of each pair of non-adjacent vertices? Let's take any pair of non-adjacent vertices. We know that the degree of each of those vertices will be more than or equal to n by 2. hence the sum of degrees will be more than or equal to n, hence definitely more than n minus 2, and hence we can say that if this is true then this is true, and if this is true then the graph is connected. So we have proved lemma 1, and using lemma 1 we can say that in our original problem we know that G is connected. Now we only need to prove that it's Hamiltonian. We already know that G is a connected graph and minimum of the degrees of all the vertices is greater than or equal to n by 2. Now there will be so many paths in the graph G, and let's take the largest path among all of them. There may be more than one largest paths, so let's just take one of them. There might be two largest paths, there might be more than two also, but we'll only take one largest path. So let's assume that that largest path is V0 to Vk, V0, V1, V2, V3 up to Vk. This is a path. Path means this means that V0 is adjacent to V1, V1 is adjacent to V2, V2 is adjacent to V3, like that. So now if we observe carefully we can see that any node that is adjacent to V0 must be on this path. If that node is not on this path, then we can connect V0 to that node, and this path P will not be the longest path. The longest path will be the one which will contain that extra node. So there cannot be some extra node which is not on this path but is adjacent to V0 or to Vk. Okay. Now let's take this is the path. Okay. Now what do we need to prove? We need to prove that it is a Hamiltonian graph. In other words, there's a cycle. Hamiltonian graph is a cycle that takes all the elements of the graph on it, and each node is visited only once. So let's see what happens if there exists a J such that the value of J is greater than or equal to 0 and less than or equal to k minus 1. So let's say between 0 and k minus this node, between this node and this node, there is some node called Vj, including it can be here also, it can be here also. Let's say there is a node called Vj. So obviously if this is Vj, then next one will be Vj plus 1. And such that Vj and Vk are adjacent to each other. Vj and Vk are adjacent to each other, and Vj plus 1 is adjacent to V0. So if these two are adjacent to each other, what will happen? If that is true, then we can see that there is a cycle. We can see that there is a cycle, this cycle. Which will cover all of them. So because our assumption is there is no cycle, so obviously there cannot be such Vj. So if that is true, then what will happen? Then basically if V0 will have a lot of neighbors, V0 will have at least n by 2 neighbors, you know that. So among all of these nodes, V0 will have a lot of neighbors. So if V0 is neighbor with any one of them, let's say it's neighbor with V2, then obviously V1 should not be neighbor of Vk. Otherwise this cycle will exist, which we have already assumed that we don't have a cycle. Okay, so if there is no cycle, then any neighbor of V2, any neighbor of V0 will basically disallow the node preceding it to be neighbor of Vk. If V0 is neighbor of V0, then if V2 is neighbor of V0, then V1 will not be allowed to be neighbor of Vk. Although V2 can be neighbor, but V1 cannot be. So it means for every neighbor of V node, there will be one node which will be disallowed to be neighbor of Vk. What happens? What are the consequences of this? To understand the consequences, let's divide all these nodes into different parts, different groups. So on path, all the vertices on this path can be divided into following 4 categories. 1, the vertices which are adjacent to Vk. So the vertices that are forbidden to be adjacent to Vk because the vertex to the right of these vertices is adjacent to V0. So if any vertex is adjacent to V0, let's say Vj plus 1, then Vj will be forbidden to be adjacent to Vk. So there will be a lot of such vertices which will be forbidden to be adjacent to Vk. And then the vertex Vk itself. And the fourth one is any other vertex. So there may be some vertex which are not forbidden to be adjacent to Vk, but they are also not adjacent to Vk. So we don't know what is the number. That number in the fourth category can be 0 or more, but we know what will be the number in the other 3 categories. The number in category 1 will be equal to degree of Vk. Okay. The number of vertices in category 2 will be degree of V0, and in the third category there will be only one node which is vertex Vk, and the fourth category will have unknown number. If we add all these numbers, we know that degree of Vk is greater than or equal to n by 2. We also know that degree of V0 is greater than or equal to n by 2 because this is given in the theorem. If we add all these vertices, if we try to find out what is the total number of vertices on this path, that will be equal to greater than or equal to n by 2 plus n by 2 plus 1, which means it will be greater than n plus 1. If it is greater than n plus 1, then obviously that's impossible. That is why our assumption that there is no cycle is not true. It means there's definitely a cycle. Okay, if there is a cycle, then we already know that whatever is the longest path, we just have to find that longest path, and then existence of that path itself would mean that there will be a cycle which will have only one, each of the node on it only once. Okay, now do we know that there is no other node left? Do we already know that this longest path covers all the nodes on the graph? Probably not. So let's assume that there is some other node which is not on this path, which is not on the longest path. What will happen then? Let's assume that there is a node u which was not on the original path. But we already had proved, first of all, what was the first thing we proved? We proved that it is a connected graph, which means every node in the graph will be connected to the other nodes, at least one of the other nodes. So u will be connected to, let's say, another node called w. If u is connected to w, then there exists a path which starts from u and then goes to w and then here, and then it goes like this and then comes and stops at the node which is exactly next to w. That would mean, what will be the length of this path? The length of this path will be more than the length of our original path p, but that's contradictory to what our assumption was. We assumed that p was the longest path, hence there cannot exist a u outside this path. Hence we know that all the nodes of graph G are on this path, and there exists a cycle, which means there is a Hamiltonian cycle in this path and the graph is Hamiltonian. Hence proved. Thank you for watching.